this session is Sofya Raskhodnikova. She will be talking about erasures versus errors in property testing and local list decoding.
So my name is Sofya Raskhodnikova, and this is joint work with Noga Ronzevi from Haifa University and with my student Nitin Varma, who is wonderful, and he's graduating and looking for a postdoc. So please look at his CV. Okay, so our main motivation for this line of work was to study sublinear algorithms that are resilient to adversarial corruptions in the input. And specifically, we'll focus on the property testing model. So this is kind of a standard picture of a randomized algorithm. So the way I usually think about it, so it's, of a sublinear time algorithm. So the way I usually think about it, well, it's a randomized algorithm that gets a very, very long input. And it's allowed to probe some locations in the input, so query and get back the what's written in this location. Then it runs for a very short time and outputs an approximate answer. And our goal is to study the quality of approximation versus the resources that the algorithm uses. So for example, the number of queries or the running time. However, so the question that we asked was, is it always reasonable to assume that the input is intact? So it could be the case that there are errors in the input or erasures. And so these are the types of corruptions that we're going to consider. So it could be the case that the algorithm, while the algorithm is running, it's getting wrong answers to the queries. So specifically, we wanted to understand what happens when there are erasures in the input. So in this case, there is some parameter alpha given to you. So you know that there is at most alpha fraction of the input that's erased. And in the case of errors, at most alpha fraction of the input is modified adversarially before the algorithm starts running. And the algorithm does not know in advance what's erased or modified. So when it queries the location with the erasure, so it gets back, well, no, you're not allowed to know what's written there, or it's erased. So can we still perform the computational tasks that we want to perform? In particular, we'll focus on property testing. So this is the property testing model that we all know and love. So it was first considered by Rubenfeld and Sudan and formally defined by Goldwasser and Ron. So we, in this model, so our randomized algorithm has to solve a decision problem, approximately. So the answer to the actual problem is yes or no. And the algorithm has to accept with probability at least 2/3 if the answer is yes, and reject with probability at least 2/3 if the answer is far from yes. And specifically, the distance is measured in terms of the fraction of the input that has to be modified to make the answer change from no to yes. Okay, so this is the standard property testing model. And in the middle here, when the input is epsilon close to being a yes instance, we don't care what the algorithm outputs. So the analogous model for testing with erasures is as follows. So we have our parameter alpha. So we have at most alpha fraction of the input bits erased, or input characters erased. And so we want to answer yes if we can fill in erasures in such a way that the answer could have been yes. And if any way we fill the input, we fill in the erasures, the answer is far from being yes, then we want to say no with high probability. And otherwise, we don't care. And so now there are two parameters, so the fraction of erasures and the distance, which is our approximation parameter that we care about. Are there any questions about the model? Yeah.
So here, I mean, the sublinearity is crucial because otherwise I could just do all the possible completions and test them, right?
Well, so okay, so it depends. So the question is whether if the sublinearity is crucial, because otherwise you could just try all possible completions. So yeah, so the question is also whether you care about just the running time or the query complexity, right? So if you care about the query complexity, so once you read the whole input, you can figure out whatever you want, right? So, but we could also care about the running time. Good question. Any other questions? Okay, so what about errors? So the appropriate model is called tolerant property testing, and it's been defined by Parnas, Ron, and Rubenfeld actually much earlier than this Erasure-Resilient testing. So here, if we think in terms of adversarial corruptions, so we can just say, okay, at most alpha fraction of the input is incorrect. And analogously, we want to say, so we have our yes instances and instances which are epsilon far from yes. But now we could also have alpha fraction of our input incorrect. So what we ask is to accept with probability at least 2/3 if we are alpha close to a yes instance, right? So if we need to change at most alpha fraction of the input to get to some input on which the answer is yes. And if we're epsilon far, then we would like to reject. Are there any questions about the models? So what are the relationships between the models? So alpha epsilon tolerantly testable is the smallest class, so this is the hardest thing to do. And alpha erasure-resiliently epsilon testable is a bigger class, so you can think, so it's obvious that tolerantly testable is contained in erasure-resiliently testable because you can just fill the erasures in arbitrary ways. So it's obvious that this class is contained in this class. And epsilon testable, right, so is yet a bigger class, right, so also it's contained, so this one is contained in the bigger class for obvious reasons, but it's less obvious whether containments are strict. And it turns out that they are strict. So Fisher and Fortnow separated standard testing from tolerant testing. And so when we defined this erasure-resilient testing, we separated it from standard testing. But so the question that remained was to separate tolerant testing from erasure-resilient testing, and this is what I'll show you today. So specifically, there exists a property of n-bit strings and ranges of parameters alpha and epsilon such that this property can be alpha resiliently epsilon tested with constant query complexity, meaning the query complexity of the tester depends only on alpha and epsilon, but not on the length of the input. But the same property, in order to be tolerantly tested, requires many queries. So in particular, polynomial in the length of the input. Are there any questions?
So for the standards, so the separation from erasure to just standard testing, it's a similar result?
Of the similar form, right? So so there it's basically, it's linear actually. It's omega tilde of linear. At least, so maybe not the way we've written it, but we know how to make it linear. And
is it a natural property in some sense, or is it a little bit like the Fortnow?
Yeah, so it's not natural, so it's constructed via PCPs, right? So I'm going to show you. So it's yeah, and it's a good question whether you can do something like this with a natural property. And, yeah.
So the Fisher-Fortnow separating example should be a separating example of one of the two.
So basically, it was almost a separating example for. So let me go back. For testable versus erasure-resilient testing. So it's just a kind of a small note in the paper that defined the resilient model, erasure-resilient model. Right. So, but we weren't sure how to separate this. Any other questions? So, so this is what we'll talk about today. But most of the talk, I'm going to describe constant versus something that depends on n, but has very weak dependence on n, and then I'll mention what's needed to make it into polynomial. So n to some constant r, inverse polynomial. Okay, so the main tool is locally list erasure decodable codes. So I'm going to show you the separation, but let me just talk about this. So locally list decodable codes have been studied extensively. There are many papers. But so when we basically decided we need the same codes with erasures, to our surprise, we didn't find anything. So with these two constraints, so we wanted them to be locally, which I'll explain, and we wanted them to be able to handle lists, right? So to be able to output lists. So in this context, only errors, not erasures, were previously studied. And it's not the case without the locality restriction. So if you look at list decodable codes, then they did study both errors and erasures. So the question that kind of we wanted to answer for our separation was, can locally list decodable codes perform better with erasures than with errors in some respects? So let me define what the locally list erasure decodable code is. So this definition is basically the same, or just except that there are errors, erasures, not errors, as the standard locally list decodable code. Okay, so an error correcting code is a map from message space to the code word space. So here we have parameters alpha, which is the bound on the fraction of erasures, list size, which is the bound on the size of the list, and q, which is a bound on the number of queries that were allowed. So the input to the algorithm is a code word, and it can have erasures, right? So buttons denote erasures. So the first condition is that the fraction of erased bits in the input has to be at most alpha. So then the algorithm itself, the local list erasure decoder, is allowed to query some positions of the input word, and specifically at most q positions. Then it runs for a short time, and then what it outputs is a bunch of other algorithms. Right? So at most L of them. And each of these algorithms basically is an implicit representation of one of the decoded code words. So this is the actual condition that we want. So with a high constant probability, for every message whose encoding agrees with our input on all the non-erased bits, we want to make sure that one of the algorithms implicitly gives this code word. Okay? So for every code word that could have been obtained, could have been mapped to this by erasing some bits, we want to make sure there's some representation, some decoding of it. And the decoding is one of these algorithms. And so what do we want from this algorithm? We want to make sure that this corresponding algorithm, if it's given oracle access to this input, it will be able to decode required bits. So I can ask it, what was the ith bit of the original message, right? And it's supposed to answer with high probability correctly. So this is the main requirement, right? So, and again, so we have a list of algorithms here as opposed to the list of actual code words, because code words are huge, right? So this is the local model. And so the final condition is that each algorithm is also local. It makes the most Q queries. So this is locally list erasure decodable codes. And so the local list decodable codes are defined the same way, except that you can have errors. So let me talk about the Hadamard code. So this is the a code which is very good locally list Erasure-Decodable code, except that it has low rate. So we're going to use it in our example. So the Hadamard code maps k bits to 2 to the k bits, and given input x, which is a k-bit vector, it maps it to all evaluations of the linear function with coefficients being x, right? So x, so this function evaluated all points, all points y. So, and this code is actually impossible to decode when the fraction of errors is greater or equal to 1/2, because basically all code words have distance 1/2, relative distance 1/2. So, so let's try to understand how easy it is to decode this code. So with errors, so local list decoding of Hadamard code is the famous result by Goldrich and Levin. And basically what they showed is that for any fraction of errors, which is up to 1/2, but it cannot be more than 1/2, so up to the bound that you can achieve, you can locally list decode it with lists of size 1/1/2 minus alpha. So this is how close we are to the 1/2 threshold. So that's squared, and the similar number of queries. And it turns out that both of these functions are tight, right? So you cannot go below this in terms of list sizes or in terms of the number of queries. So we try to understand the same code with respect to erasures. So you can have more erasures than you can have errors. So you can get for any alpha, which is some constant below 1, you can have that number of erasures, and you can decode even with a huge number of erasures. And so here, the difference is that we don't have square, and so this is also how close we are to the threshold, to the bound with which we can still decode. And the same bound here. And it turns out that the number of queries is actually tight, and it's implicit in the recent paper by Greenberg, Chatiel, and Viola. But the list size, we're not sure if it's tight. And so notice that these are better dependencies here than here, so there's no square. And so improvement in dependencies.
Is that in Erasure, you know that you're not given, that it's a faulty query, and in the
Yes.
errors, you don't know which errors are faulty.
Yes. So that's the kind of the original hope was that you can get lots of advantage from it. And in the case of Hadamard code, you can get advantage. But so there are bigger questions that remain. So basically, how much advantage you can get? Can you actually get a drastically better rate with those codes? Great. So you can see when there is an erasure, you can see it, that it's an erasure. And so, any questions for this? Okay. So what does it have to do with the original property testing question? So how does separating erasures from errors in local list decoding help with separating them in property testing? So let me start by kind of giving some building blocks which go into separation, and then I'll show you the picture. So there are some properties which are very hard to test, but easy to decide exactly. So one example of such a class of properties is 3CNF properties. So here we given a formula on n variables. So it's a 3CNF formula, and it has a linear number of clauses. And the property that we want to consider, it's we want whether our input satisfies the property or not, is a set of satisfying assignments to this formula. Right? So these are our yes instances. So it turns out that there is a class of formulas like this, such that epsilon testing this class of formulas requires a linear number of queries, right? So which is as hard as it gets in this sublinear world. However, it's easy to see that if you want to decide exactly whether our input satisfies this formula or not, you can do it in linear time, so for any 3CNF formula. And so there is a linear size circuit that decides this property exactly. So this is a special class of properties that we're going to start with. So another component that we're going to use is PCPs of proximities. So think about testing with advice. So this PCP of proximities, or abbreviated as PCPPs, were defined by Ben Sasson et al. And simultaneously by Dinur and Reingold. So basically, we have a PCP verifier, which is a sublinear time algorithm, and it gets input to the original, it gets query access to the original input, and query access to some proof string. And if the original input has the property, then there has to exist a proof for which the verifier accepts with high probability. However, if the input is far from having the property, then no matter what the proof is, the verifier has to reject with high probability. Okay, and we don't care what happens on the inputs which are in between x and, so between the property and epsilon far from the property. So what they showed is that every property which is decidable with a circuit of size m has PCP of proximity of length roughly linear in m and constant query complexity. So in other words, question? So in other words, so what does it imply about testing 3CNF properties? So it turns out, so basically, okay, so we know that if we want to test this class of properties, we need a linear number of queries, so without a proof. But if we have a proof, we can test it with constant query complexity. And the proof that we need is roughly of linear size. So we have this interesting property, which is easy to test with a proof, but very hard to test without a proof. So somehow we would like to amplify it to get the separation that we want, so to kind of translate it into our setting. And so this PCP idea is from kind of Fisher and Fortnow. They used a different class of properties, but basically they kind of their starting point was a similar type of separation. Okay, so now, so in our separating property, we're going to use the code. So specifically, we'll try Hadamard first. So this is the property. So we're going to define it as follows. So first part of the property of the input string is called the plain part. So there we just will take some string x that satisfies the hard 3CNF property. And we're just going to repeat it a certain number of times. So we're going to repeat it to balance these two parts. So we want this part to be a constant factor larger than the encoded part. So we want it to be really hard to make changes to this input x, in the sense that you have to pay lots in the distance if you make changes in x. Okay, so and the second part is just going to be the encoding of the string x and the proof. So pi of x is the proof on which the PCP verifier accepts x. So in order for the string to be in the property, in the separating property, x has to be in the 3CNF property, right? So if it's in the 3CNF property, then there is a proof on which the verifier is going to accept. So pi has to be that proof. And then we take x concatenated with the proof, and we just encode it with the locally list Erasure-Decodable code. So for the purposes of this talk, we're just going to use the Hadamard code. But if we get a code with a better rate, then it implies a stronger separation. So this is the property. Any questions about the property? Okay, So, so now we would like to show that we can actually test it with an Erasure-Resilient algorithm. And the idea is that if a constant fraction, so let's say 1/4 of the encoding is preserved, we can still locally erasure decode. So here's a kind of high-level overview of the tester. So it's going to locally list erasure decode the Hadamard encoding, and it's going to get a list of algorithms. And so for each algorithm, it's going to check two things. So first, it's going to check whether the plain part, so the first part, is actually repetitions of the decoded X. And it's just going to do it by sampling random bits, right? So it's going to query our decoding, right? So our decoding algorithm on some random bits of X, and it's just going to check with the corresponding random bits here to make sure that they're actually repetitions of X. And it's also going to check that the PCP verifier accepts this X concatenated with the pi of X, which is implicitly decoded. In order to do this, it's just going to run the PCP verifier, which is going to ask a constant number of bits. So it has to decode only a constant number of bits here also. And then at the end, it's going to accept if some algorithm on the list satisfies both checks. Right? So when we run with that algorithm, everything worked out. So both checks passed. Right? So this algorithm has query complexity, constant query complexity. Right? So again, just to do both checks, we only need to decode a constant number of bits. Right? So we'll query each algorithm on a constant number of bits. Any questions about this?
So don't you need to check whether pi of x is also the proof of this x? So you said you can check whether this x, these two are equal to each other?
Yeah, so this is the second check. So the first check actually makes sure that these are repetitions of this x, indeed, right? And the second one checks that, so this proof is actually accepted. So this is the second check. Okay, so actually, so let me maybe say a few words so I don't have like a detailed proof why it works. So let me just kind of tell the intuition. So if actually we have a code word, so if we have the input which satisfies the separating property, then the checks are going to pass, right? So there's going to be some algorithm on the list of the decoded algorithms for which we actually have the original input, which satisfies the property. And for that algorithm, we're actually going to pass both checks. Right? Does it make sense? So, and the slightly harder to prove thing is that if our input is far from satisfying the separating property, then it's going to imply that what we have here is the repetitions is far from being a repetition of some string x, which satisfies the 3CNF property. Right? So because this part is slightly longer, or a constant factor longer, basically there has to be lots of mistakes in this part. And then one of these two checks is going to fail, at least one of these two checks is going to fail for every single proof. Right? So for every single decoding of x and the proof. Okay, so this was the algorithm itself. So now what's the idea of why it's hard to test tolerantly? Well, the idea is that we can reduce standard testing of the 3CNF property to tolerant testing of the separating property. So why is this? So given a string x, we can just simulate access to the repetitions of x plus just all zero string. Right? So all zero string is, in fact, can be viewed as a Hadamard, any Hadamard code word with half of the bits incorrect, right? So half of the encoding is corrupted. So if our tester is supposed to handle such a high rate of encoding, then it's supposed to be able to tell us whether the original string X is in the free CNF property or far from the free CNF property. However, we know that without advice, just testing free CNF property, right? So this is just testing without advice, right? So it requires linear number of queries. So therefore, in order to be able to test this, we have to do number of queries, which is logarithmic in this, right? Because we encoded, we blew up the length of the input, so by making it 2 to the original little n, right? So we still need little n queries, right? So, but this is log of the length of this whole input. So this is the idea. So what we proved is that the separating property is erasure-resiliently testable with a constant number of queries, but it requires some number of queries which depends on the length of the input to test tolerantly.
Can I ask a question? Sure. So normally there's always, so here your erasures was 1/4 and your errors was 1/2, right?
So
I mean, your example is, maybe you can do better. So you.
So we're comparing apples to apples actually. So therefore corresponding parameters, alpha. So it was. Let's see. Sorry. Yeah, I guess we can. So if I make half of these bits, we can make them half, both of them. Right. So they have to. Sorry, I guess I didn't put the same thing on the slides. So let me go back to the quarter. So it can be for any constant here, right? So yeah, you're right. So I should not have put a quarter here, right? So we can put half there, right? So if we have 1/2 of the encoding, right? So we can still decode. In fact, we can decode for any constant as long as we have any constant preserved, which is constant fraction of the original input, right? Good question.
Yeah, but on the other hand, I mean, so you, okay, maybe we'll have an offline discussion.
Right. So yeah, so the results actually have work for the same, for the corresponding parameters, right? So for the corresponding alpha and epsilon, for which they, for which it
I
makes
guess
sense.
my question is when you're doing error correction, if you corrupt half,
Right.
you generally cannot recover anything, right? I mean, that's what you use.
Right, so that's the point, right? So if you corrupt half by introducing errors, you cannot recover anything, right? So basically, we're equally close to
So
any
the more
correct.
interesting case is when the error rate is less than 1/2, right? With
So for the errors,
yeah.
right? So but what we're using is exactly the fact that with the same error rate, you can decode if the with the same corruption rate, we can decode if the corruptions are errors, but we cannot decode if the corruptions. Sorry,
The other way around.
the other way around. We can good. Somebody's paying attention. So we can decode if the corruptions are erasures, but with the same rate, we cannot decode if the corruptions are errors. So this is exactly what we're using.
Because in,
Well, in a sense, like erasure is like it's modified, but then when you read it, it says, well, actually it was modified, so you see it was modified.
you know what,
so,
when it's wrong.
in a sense.
Yeah, no, I know about that.
So it's not surprising. You're saying it's not surprising,
Yeah,
right? So
I guess.
so this is what we were hoping for. So when we looked at this, we said, okay, if we have a code like this where you can decode with the erasures, but you cannot decode with corruptions for the same rate, then we're done. But so it turned out that nobody studied these things, and moreover, it's not so easy because there kind of there's locality involved here, and so I'll get to the open questions. So I guess there's a big open question whether you can improve on the rate, right? So.
I guess, yeah.
Oh. Any other questions? Oh, so this is what we proved. So tolerant testing is harder than erasure-resilient testing in general. But I guess this log n is a little bit disappointing. So what we want to get is n to some larger power. Okay, so what are the challenges in trying to strengthen the separation? So what I mentioned before is that if there exists a code that is locally decodable from an alpha fraction of erasures with the following conditions. So this list size and the number of queries are constant, right? So they only depend on alpha. And it has rate, which is this little n over big N, right? So which is inverse polynomial. Then there is a stronger separation, right? So constant versus n to the c. But the problem is that the existence of such a code is an open question. And more specifically, the corresponding question for the case of errors is the holy grail of the research on local decoding. So this is what they're trying to get. So there are actually better, slightly better codes with slightly better rate than Hadamard, but they're not good enough. And they're stuck there. So I guess the one big open question is whether we can do better with erasures. So if the erasures are obviously easier, then maybe somebody can come up with a code that actually has inverse polynomial rate, so all these conditions, but with erasures. Okay, and then we would be done. Okay, so but we couldn't do this, right? So because we didn't break this open question. So this is what we did instead. So first of all, there is an observation that queries of the PCP verifier can be made nearly uniform over the proof indices. So basically, the verifier can be made in such a way that it just samples what it needs to sample nearly uniformly. So for appropriate definition of nearly uniform. So there is no need to be able to decode every single bit intuitively. So the idea, the main idea in the strong separation is to encode the proof with the appropriate least locally decodable codes that decode a constant fraction of proof bits correctly. So they don't decode the whole proof correctly, but there is a constant fraction that they can decode correctly. So there is a guarantee that they decode at least a constant fraction. And so approximate locally least decodable codes of an inverse polynomial rate are actually known. And they've been used in other contexts. So we use such a code. And so one observation is that if you have a code that works against errors, you can make it work against erasures with asymptotically the same rate, and you can have twice as many erasures. You can handle twice as many erasures as you can handle errors. So why is this? So if you have your erasures, you can basically fill the erasures with uniformly random bits, and then in expectation you're going to get half of them correct, and then you can use the approximate least locally decodable code. So once you have a good least locally decodable code, you can get a good least locally decodable code that works against erasures. So you can get what we need. But the problem, so I guess one of the questions is, do you actually need a code that works against errors in order to get a code that works against erasures? So it's possible that there could be better codes that work against erasures. So let me talk about open questions. So unless you guys have more questions. Okay. So first open question: can we get even stronger separation? So constant versus linear. Oops. Some kind of erasure, I guess. Okay. So this is what we have in the other two separation cases. So at this point we have constant versus linear. But so here what we actually get is constant versus n to 1/5, and this is basically depends on the rate of the code that we used. So another question is what Clément asked. So can we get the separation for some natural properties? So this property is that we use are artificially constructed. Another question is, so other questions that have to do with least locally decodable codes. So locally least erasure decodable codes provably better than least locally decodable codes. So we actually kind of showed that for Hadamard, so in terms of the list size and the query complexity, we can do better. But kind of the big question is, can you get list locally decodable codes that work against erasures with much better rates. So we know that if you have a code that works against errors, it implies the code that works against erasures with twice as many corruptions. But is the implication true the other way? So if you can handle erasures, is it true that you can also handle errors, or can we do much better? So I guess I would say this is a big open question. And I guess constant query, constant list size, local list erasure decodable codes with inverse polynomial rates. So this is I mentioned this is a big question for errors, but maybe perhaps way to attack it is to look at erasures, right? So maybe it's a simpler question. Thank you.
I'm not quite sure the question makes sense, but have you studied that kind of model where you don't look at arbitrary testers, but like testers that only get sample-based testers, or that kind of weaker kind of models? Is sample-based testing easier to separate from regular?
So the question is, can you do it for sample-based testing? Can you separate? Oops, getting erased. So I'm not sure. So I guess you can ask similar questions for other models. So we did it for property testing, right? So, but you can say for other, you take your favorite model of computation and ask, is it easier to deal with erasures than with arbitrary errors? So I guess I cannot answer this off the top of my head, but yeah, maybe it's easier to separate.
What is the situation for graph property testing?
Oh, very good question. So we are trying to understand for graph property testing. So we're working on this with Nitin and Ramesh, two of my students, and with Amit Levy. So we have some results. So there are some interesting threshold phenomena there. Oh, okay. So the first thing with graph property testing is some issue that I kind of put under the carpet here. So, but if we go back to the definition of Erasure-Resilient testing, so the way I defined it on the slides is actually different than the way we define it in the paper. But it doesn't matter for functions, and it matters for graphs. So let me get back there. Sorry for clicking through this. What basically, so I said, okay, so we want to say yes if it can be completed to something that has the property, and we want to say no if it's, we want to reject if any completion is far from satisfying the property. So how the farness is measured, so is it measured with respect to the whole string or just with only non-erased part? So for function properties, it doesn't matter, but it turns out for graphs, it does matter. So basically, so for functions, it doesn't matter because you can fill this the way you want and there are no restrictions, right? So if there are erasures, you can just fill it the way you want. But for graphs, basically, there could be some restrictions. So if I, my graph is represented in the adjacency lists model, then so if I have an erasure for some vertex, it means it has to connect to something, right? So there is some restriction on how things have to connect, and it's not the case that you can connect them in an arbitrary way. So there are some interesting questions right there already. And basically, we look at some simple properties, and there are some interesting threshold phenomena. So basically, at some point, you for certain values, you cannot test at all, and then when alpha drops becomes sufficiently small, then you can test very well. So there is some kind of threshold phenomenon there. So but we studied only a couple of properties so far.
Okay, let's thank Sofya again.